Our next speaker is Jeff Fowles, who's a Principal Advisor in Toxicology at MPI. Welcome, Jeff.
Can you hear me? Yeah. Okay. Kia ora koutou, katoa. I'm Jeff Fowles. I'm a Principal Advisor of Toxicology with New Zealand Food Safety at MPI. And I'm going to be talking to you about, again, food packaging from a toxicology perspective. And the title of the talk is Precaution and Optimism. I think that there's ample room for both in this space. And it's an interesting time to be working in this area in toxicology because of all of the new innovations, the regulatory challenges, the debates, the active, lively disagreements amongst regulatory authorities and so forth over the toxicology of some of these chemicals that exist in and have existed in the past in food packaging. So it's against that context that I'll give my talk. As previously mentioned, we very much rely on food packaging polymers. They've generated for us a revolution in food safety. Decades ago, they provide barriers to gases, microbiological and chemical contamination and physical damage to food. They maintain freshness and prevent loss of flavor and aroma and nutrients, and it's allowed a great deal of expansion of commerce domestically and internationally. So they're very, very important things. At the same time, we have a burgeoning plastic waste problem globally, of which only about 20% is food packaging materials, but it's still a significant contributor to the overall problem we're facing. And the United Nations Environmental Program and other countries, many countries have implemented policies and programs to start requiring recycling to try to reduce and also to seek alternatives to reduce plastic inputs to the environment. And the polymer types, there are the thermoplastics, the so-called polyolefins, which are polyethylene, polypropylene, and polyvinyl chloride, polyesters, polylactate, PET, polystyrenes, and then other types of plastics which are called thermosets, which are polycarbonates. Anyway, there's a lot of details to the different sort of classifications of these materials. And they each have sort of their own separate considerations. So the devil is kind of in the details about each one of these and what the issues are that they present. The issue of the advent of biopolymers is an exciting new area with the chitosan, starch, and protein-based polymeric materials, the so-called smart polymers. You'll see if you look in the literature about edible polymers. But they also have chemistry that requires, in many cases, the addition of additives to give them the functionality that they need to replace the older materials that we currently have. So from the consumer perspective, we have these 7 different categories. Only 3 of them are recyclable at the home. The PET, the high-density polyethylene, and polypropylene plastics. The other ones require specific facilities to recycle, so it's not so convenient for those polymer streams to be recycled. And so keeping them pure is a challenge, and we also have the additional issue of paperboard boxes with coatings, also an important area of food packaging chemistry. And the basic issue is that we're looking at migration of chemicals from the packaging, but also from the external environment, and these are all governed by migration limits that are set for specific types of chemicals in different kinds of polymers. And measured analytically, these migration limits are connected to health-based guidance values in many cases, but not necessarily directly connected. They're also connected to feasibility. And then the chemicals we're talking about that are sort of the usual suspects that get mentioned a lot are predominantly the plasticizers, notably the phthalates. BPA is, and its relatives are also an important area of disagreement amongst authorities on the health significance of traces of BPA. The non-stick PFAS compounds, which have given us, this is our latest lesson in the seemingly over and over again lesson we need to learn about developing long-lasting chemicals that we later have to phase out or ban because of functionality sort of leading the way in terms of ahead of public safety. But the PFAS chemicals are an interesting one because they are being voluntarily phased out, have been voluntarily phased out in New Zealand food packaging as of last year. And we're going to have a chance to have a look at that this year with a couple of surveys we're doing at NPI. So some of these are intentionally added, some of these are unintentionally added. They find their way back into polymers from other polymer recycling streams. Luckily, temperature will take care of some of these, but not others. So the bisphenols and the phthalates tend to degrade around 250 degrees Celsius, 260 degrees, and if we're going to go the route of thermal degradation, as was previously mentioned, that will tend to go up around 400 degrees. So these chemicals will be reduced to base constituents. The PFAS are a different story. They're more recalcitrant to thermal degradation. I'm going to skip this over, but just briefly to show that bisphenol A, phthalates, and a lot of these other environmental contaminants do have at the core of the discussion about them impacts on oftentimes infertility and puberty developments at higher doses. The question has always been about what happens at ultra-trace low doses and how much do these findings contribute to sort of a general sense of chemophobia in society. So we want to shift the discussion from hazard to risk-based in these sort of spaces because I think there's a lot of needless fear that's generated from some of the publications and positions that are taken internationally. There is a database that's been developed by the Food Packaging Forum, which will allow you to survey. It's a sort of a clearinghouse of literature. You can go and have a look at thousands of different publications and entries on different food contact chemicals. And again, it's a way to target specific questions to see what's published in these areas. It's a fairly interesting dashboard. It's publicly available, something you can have a look at. In terms of what you can get out of this database, I don't know if you can see that very well. It basically tells you the polymer type, the kind of chemical, the kinds of entries, what the hazard considerations are. It's very much a hazard-driven database, so there's no element of risk assessment in this. It's just telling you what the chemicals are, what their hazards are, and it's essentially designed to align with the European Chemical Authority's hazard assessments. So, as I mentioned, the role of recycling includes thermal decomposition, and so this can degrade a lot of these chemicals that are found in the plastics. PFAS needs a bit higher temperature to degrade over 350 degrees C. That's with the presence of a catalyst. Antimony is something that's found in PET as a result of its presence in catalysts for the production of the polymer, and also in some cases as a flame retardant. So antimony does not degrade thermally and does have to be managed with the PET recycling process. It's not a major hazard or risk, but it's something to consider. In terms of discriminating between PET types, virgin versus recycled, there are some new publications coming out that are attempting to do that with machine learning, combining with non-targeted analytical techniques to see and verify basically whether the PET is in fact virgin or recycled. So, yeah, the plastic pollution problem really requires systemic thinking that shies away from quick fixes and only addresses one symptom of the problem. If we start to require recycling to a degree that we start to introduce unintended substances into the plastic packaging, we could contribute to the perception of public health risk from these chemicals in the food supply. So it's important to remain vigilant and to have surveillance projects that will enable us to have hard data on what the levels of chemicals are in our foods. The New Zealand Total Diet Study, which we're in infants and toddlers, is going on this year and the first part of next year, building on the really great work that has been done historically by ESR and DSIR before them, looking at a broad spectrum of foods in New Zealand for different kinds of contaminants. This is the first year we will have included food packaging contaminants specifically in the TDS. And there they are, the PFAS, phthalates, bisphenols, and antimony. We'll have a few other contaminants in there that are new also. The PFAS in New Zealand foods, we have some data on PFAS in New Zealand diet, but it's targeted samples from the previous TDS. And in that case, we did not find, there was only one finding out of 96 food samples measured, and that was theorized to transfer from packaging, but the dietary risk was considered to be negligible. We did not get any detects for PFOS, PFOA, or PFHXS. Phthalates are considered to be highly prevalent, but are there really risks? We looked at and found 2 samples out of 74 targeted samples from the previous TDS and found that they were only a fraction of the TDI in the worst case scenario. So again, they are prevalent, but they don't really rise to the level of significance in terms of risk. And a similar assessment done by EFSA in 2019 found that a grouped analysis of these substances also did not rise to the level of significant risk, being about 7-fold below the TDI in Europe. So we need to remain vigilant, but that doesn't mean that there's a 5-alarm fire. We just have to have readiness to collect data and have the data in hand when we start looking at the changing pictures of these polymers as we go forward. Oops. One of the big controversies in regulatory toxicology is about bisphenol A. And this was reviewed and reissued with an opinion by EFSA last year, where a previous, here you can see the animal dose response on the right from the toxicology studies, and the estimated extrapolations to human dose response with the margins of safety, shifting the dose response way to the left. And it was thought at the time that the tolerable daily intake was very conservative at the time, but then more recently, EFSA bumped it down 10,000-fold more to 0.04 nanograms per kilogram per body weight, basically amounting to a de facto ban on bisphenol A because it's down to a level that can no longer be quantified reliably. So that's a subject of hot debate and discussion in regulatory tox circles, whether this is justified or supported, but that is what the European assessment is. So hazards, yes, but risk. It doesn't appear that we have a risk at the moment from these substances. Phthalates, PFAS, and BPA residues have not risen to the level indicating a significant risk. We do have these BPA alternatives, which are being used to fulfill the same function, and they have less robust data sets to characterize their hazards, but they overall seem to be of less potent hazards. So that's a good thing. PFAS are voluntarily being phased out by a lot of industries, and that's likely to continue given its persistence and its continued inputs. It's going to be with us for a while, so we have to be aware of what the levels are. And antimony and PET, we've detected it, but levels are below the drinking water standards, so it's not a risk either. So we have some really general advice at MPI how to reduce exposures to food contact chemicals. Namely, don't wash plastic bottles with harsh detergents or bleach. Avoid dented food or drink cans. And don't let cling film touch food during cooking. And keep the corner of the dish uncovered to allow steam to escape. And then use only microwave-safe plastics in the microwave. And, and then thaw wrapped meats at low temperatures. So very just practical things that you can do to reduce your exposure. And I mean, that doesn't mean that there's a risk, but if people wish to reduce their exposure, these are ways to do it. So in conclusion, food packaging chemicals have been previously assessed in New Zealand as being below levels of concern. International bans and voluntary phase-outs of some hazardous chemicals like BPA and PFAS are reducing the inputs of the intentionally added substances in food packaging. Emerging replacements require assessment. Biopolymers carry generally fewer toxicological concerns and are likely to expand their presence as we go forward. Claims of reduced hazard chemical presence does require some verification and assessment. There are large public databases of food contact chemicals that can be researched, as I pointed out there earlier, through the Food Packaging Forum. But we still need vigilance on the polymers that are used in packaging that are, because of their evolution and their changing behavior at the moment. We need to follow what that means in terms of the chemicals they are bringing with them. If recycled polymer streams were to start including non-food plastics, that does have the potential to introduce non-intentionally added substances like PFAS into the food supply, so that needs to be looked at closely. Phthalates and BPA are not expected to survive high temperatures in the recycling process, in the chemical recycling process. Antimony is a known issue that can be managed and monitored. And while the risks are not currently of concern, the hazards are real, and regular surveillance of these chemicals in foods is an important way for us to ensure that the risks remain at acceptable levels. And that's everything, so thank you very much.